Hi students, this video is about measurement systems and volume. So I'm not the best person to teach you how to bake a cake or do anything really that has to do with baking. I'm not even much of a cook. My wife is definitely the cook in the house, and I'm very, very grateful for that. But I will say that I know quite a bit, of course, about the chemistry aspects of using some of the stuff that you might even see in your kitchen, because a lot of the different manufacturers that make these types of kitchenware also make chemistry equipment, and so there's an interesting correlation there. Let's say, for instance, you're making something and it asked you for 300 milliliters of lemon juice or something like that. Normally, you just turn it around and say, okay, give it to me in cups, right? Because baking is a bit more about a cup of this, a cup of that. Chemistry is a lot more about precise measurements, about measuring something in exact quantities. And even though it has these numbers on the side, this vessel isn't going to be quite what we need to do that. But if I was to try to fill that up, how would I know exactly when I got to 250 milliliters and maybe when I had gone over that or just under that? Even if I was trying to use this just to be about as accurate as I could, when do I really have this just right? Maybe you've run into this issue before, but certainly in the chemistry lab, it's very important to know how measurement works, how volume works, and really what a milliliter is. So in chemistry, we tend to use the metric system, and you've probably heard of the metric system before. It's definitely the industry standard of all the different systems that are out there, and really you would be surprised as a scientist if you found somebody using the American English units, we might call imperial units. These are not used widely by scientists, and there's a good reason for that. I'll actually try to convince you here why using the metric system is better, and then how we use it then to measure certain things like volume. So the first thing about the metric system that is so much better than the English system or the imperial system is that basically everybody else besides us already uses this as their primary means for measuring and recording information or communicating information. The examples of this, you might see like a kilometer, you might see something measured in grams, meters, degrees Celsius, though technically the one that scientists use is called the Kelvin, but still the metric unit is Celsius, centimeters, all those different units that you've seen around, but you don't really find that you would ever use them because, who else does? Well, scientists do, and also the rest of the world. And here's why they're so useful. They're mathematically convenient, and they're very easy to memorize. And I'll give you an example of a few of those things. Here's why they're mathematically convenient. All of the units can be converted from a smaller unit, like a centimeter, up to a larger unit, like a meter, by using factors of 10. When you were in grade school and you just multiplied things by, like if you knew your multiplication tables, if you were to try to figure out all the different multiplication tables, it was hard until you got to the number 10. The number 10 was so easy because you just put a 0 on the end of something, right? 5 times 10 is 50. 7 times 10 is 70. So it's very similar to that. Here are some examples. There's 1,000 milliliters, and that's a unit of volume, in 1 liter. And a liter there's about 4 liters in a gallon. That's not a good conversion because a gallon is an American unit, an English unit, but that's about how big it is. And you've got the example here of a 500-liter jar here. So if I had 2 of these, I would have a whole liter, and that's a comparison for you. Another example would be how many meters there are in a kilometer. And there's, I think, something like 2 kilometers per mile. I might have that wrong, but there's about 1,000 meters, there's exactly 1,000 meters in a kilometer, and it's very easy to convert between meters and kilometers. And then another one that's an easy to memorize factor is that water boils at 100 degrees Celsius in the metric system in centigrade, and it freezes at 0. Isn't that very convenient? That's actually on purpose. That's how it was designed. We'll see some of the kind of foibles of the imperial English standard units here, which oddly enough aren't even used in England. But the countries that use this, well, the well-known US of A, and then not knocking any of these countries, I mean, love my own, but they kind of need to get with the times. Myanmar and Liberia, and that's it. Everybody else uses the metric system, so go us. No, we should definitely get on board. And there's a lot of people who actually would support that and say that we need to change. The reason actually for it, if you're interested, is basically because a lot of times, well, one, we're used to it, but a lot of times these things are very convenient when you are using lumber and wood and different types of building materials. These units do become rather convenient. And can be hard to transition out of. So because so many things are standardized around that, we tend to stay with this. But some examples of these units that I'm sure you're familiar with: a pound, a foot, a degrees, Fahrenheit, an inch, a mile, gallons. So the problem with this is, of course, they're converted in unpredictable ways. You have to memorize each conversion rather than just memorizing a rule like factors of 10. One example would be 12 inches in a foot, right? Nobody would really know that unless you told them to memorize it, but we all tend to know that. 16 ounces in a pound. There you go, another random kind of conversion. This one blows my mind. Do you even know what it is? How many feet in a mile? 5,280. That's a good one to memorize. And then this one, do you know what water boils at? 212 degrees Fahrenheit. And of course, 32 degrees is the freezing point of water in Fahrenheit. Again, ridiculous numbers to try to memorize just because you have to, but because this is the system we use, we're so used to it. Well, in chemistry, we use these metric systems in order to do any math that we need to do and to understand the different concepts that are in chemistry. One of the things that we have to learn is how do we then deal with the stuff of chemistry, and how do we measure that? Well, we're going to talk briefly, before we talk about volume, about matter and about mass. So the first thing to discuss here is that matter is anything that has mass and takes up space. So what is matter? Matter takes up space and it has mass. So there's the two components there, mass and volume. What is mass? Mass is the amount of substance or matter that is in something. And we measure this in a particular way. We measure it on a scale, and we measure that using the gram. The gram or the kilogram, which a kilogram is about 2.24 pounds. So it's rather heavy, but certainly that would also tell you a gram, if there's 1,000 grams in a kilogram, a gram's probably pretty light. And I use grams quite often because I really like coffee. And so when I make my coffee, I put it on a scale just like this, and I measure out how many grams of coffee. And it's usually about 17 grams of coffee, ground coffee, in a good cup of coffee. So that's actually a pretty common way that I'll be using grams. But it can be hard a little bit to conceive of what a gram truly is. So here's one little trick I'll give you. If you're trying to think of how much a gram weighs, go ahead and find a nickel. I'll give you some time. Okay. It's probably hard to find a nickel. There's even a coin shortage these days. So if you can find a nickel, I'd encourage you to have one by your desk, okay? But a nickel, right, is worth 5 cents. So you probably knew that, but here's why I'm telling you that. It weighs almost exactly 5 grams. I've gone and I've put this on my coffee scale because it weighs pretty accurately in grams, and it's exactly 5 grams. And this is total coincidence, but it's a good way to remember it. If you can get a nickel and hold that and just kind of feel the weight of that, it's about 5 grams. And so if we're dealing with things in chemistry, we will be very often with things that are, 26 grams of sodium bicarbonate or 700 grams of, a sample of salt, then we actually can get an idea of how much we're talking about there when you understand how much a gram weighs. Okay, so that's trying to talk a little bit about mass and how we measure it. There's a little bit of a confusion here, though, between mass and weight. Weight depends on gravity. There's no weight in space. You're weightless, but you still have mass in space, right? So it's independent of gravity, and it depends a little bit more on like kind of your inertia and how hard it is to move somebody. You might think like in space, it's really hard to push the space station around or give it thrust or whatever because it's still heavy and it's hard to move it around. But that's not because it weighs a lot, it's because it has a lot of mass. So they are different terms. You weigh different amounts on the moon, but you have the same mass on planet Earth. So you are 50 kilograms on Earth, you're 50 kilograms on the moon, but on the moon you will weigh a sixth of your body weight. So you won't have less mass, but you will have less weight, which is confusing. And how do you measure it? Well, you'll kind of weigh a sixth of what 50 kilograms would weigh on planet Earth. You could cut that into a sixth, and you will have your about what you would feel like on the moon. So that is how weight and mass kind of are different. And you might see this makes sense in terms of like when people are on the moon and they're jumping around, kind of hopping. That is the effect of the weight being less on the moon, whereas his mass is of course the same, has not changed. So that's the difference between those two quantities. Now, if mass and volume are different, well then how does volume, they both make up matter, so how does volume work? Volume is how much space something takes up. So the amount of space that something takes up can be measured a variety of ways, but not everything takes up space in equal kind of clean ways. So the main unit we'll use is called the cubic centimeter, or is also the milliliter. And the cubic meter just be an extension of that, but it's very large. So we actually don't typically use the cubic meter. We use the cubic centimeter, which is a smaller, but actually equivalent to a milliliter. That's convenient. We'll use different ways of like measuring how big this is. You can use a ruler or tape measure to try to figure out how much volume something takes up. If I wanted to see how much volume this keyboard took up, I could measure its different dimensions and I'd be able to tell you its length, its width, its height, and I'd get you a volume. So that's kind of more like measuring a box. But what do you do for an irregular object? You'll use this process called water displacement, and this is pretty fun. So water displacement is a way to measure the volume of irregular objects, and I love this video here. This is a crow, and just watch what he's doing. Okay, did you see that? So there was a seed in the water, and he couldn't get in there, right? His beak is like not long enough and it's too narrow. He put these objects into the water in order to lift the water's level so that he could take the seed out. Now, ravens, crows, I don't know if there's a difference, but sorry, bird people, if I'm wrong, but that is a smart bird, right? What he's using is the displacement of water, water being pushed out of the way by an object in order to take out a seed and to move that seed up that was floating. So how does this work? Well, how would I measure like the volume of an AirPod? This is a giant AirPod, but how would I measure the volume of something like that? What would I do? I can't like measure that with a ruler. So an AirPod, a funny little dinosaur, whatever it is, I could measure the water displacement, and that would give me the volume. The way that this works is that you add the object to a particular device that like a graduated cylinder, and you'd measure how much the water goes up. So if I put that in there, the water is going to go up naturally because that object is taking up space. And the water can't take up the same space that the object takes up, so it gets pushed up. So as I put that object in, that water gets pushed up, and I can measure the difference between before I put the object in and after I put the object in. This is pretty simple, right? The logic makes sense, and the difference between the two is how much volume that object has in milliliters. So how do I actually measure volume in something that we'd use in chemistry class, like a glass vessel? This is a vessel called a graduated cylinder, and we use them all the time. They're really accurate. In a graduated cylinder, if you're going to fill it up, you're going to basically be in a little bit of trouble because you're trying to look at kind of from eye level, where does the bottom of that water or fluid, whatever it is, where is the bottom of that? And what happens, there's an interesting little phenomenon that when you especially pour water into glass, you've probably seen this before, it sort of likes to stick up on the side. So we always measure, scientists just said long ago, we're going to measure from the bottom of this little scoop. We call the scoop the meniscus. So we're looking at the bottom of this scoop, and we're going to try to decide, well, how deep is that? Well, in this one, we can figure out by counting each line. So this is 30 and this is 40. So this line is 31, 2, 3, 4, 5, 6, 7, 8, 9, 10, up to 40. So there's 10 graduations between 30 and 40, and that's actually where the graduated cylinder comes from. And the word graduating for graduating high school comes from the different levels of high school that you go through. Freshman year, sophomore year, junior year, senior year are going to be equidistant steps on your way to the end. So that's kind of how that word gets its origins. So how am I going to measure this? Well, 35, 36, or about 37 milliliters would be a good accurate guess here. Though I do notice the scoop goes just under 37. What do we do there? Well, scientists have actually decided that when you have two lines of graduation that you know very, very accurate, this one and that one, you can make a guess, believe it or not, on what you think that number in between is. You got to be careful with this one, but you can make a guess and say, well, it looks like it's about halfway between. So how about 36.5? That will be my number for this one. So 36.5, I think, is a good, accurate way to measure this one. The next one, we'll do some more practice. So how about 85, 86, 87, 88? There's the meniscus, 89, 90. Okay, so they're each a milliliter in between. And 88, 86, 87, 88. And, well, that's sort of in between, so I'd say 88 and a half. All right. And again, you would need to get good at this by using your, by looking at it from the eye level and really looking at the bottom of that scoop and being careful to be consistent. If you're going to measure something that would be in the middle and you're going to call it 88.5, keep saying the same number and trying to be as consistent as possible. 85, 86, 87, 88, 89, 90, 91, 92. And that meniscus really hits that line right on target. I'm going to say 92.0 because, well, we know it's not 92.1 or 0.2 or 0.3. We know it's 92.0. It's right on the dot. And that's an accurate and good way of representing that number. How about this one? Can you guess? It's going right through that line, right through the big fat 90 mark. 90.0, right? 90 and then with another 0 at the end. Make sure you include those numbers because you measured that. You knew it wasn't just 90 and a little bit more kind of up here. You measured it to say it's right on the line, 90.0. So that's how scientists measure volume, and I hope that was helpful.